Episode 65, AI Attention Mechanisms Deep Dive, How Senior Engineers Master the Core of Modern AI Systems. Welcome back to Agentic AI World, your daily edge in AI engineering interviews. I'm your host, and today we're going deep on attention mechanisms. Not just what they are, but how senior engineers reason about them in system design, debugging, and optimization contexts. This is the kind of depth that separates a good candidate from someone who actually gets hired. Let's get into it. Section 1. The problem attention solves. Before transformers, we had RNNs and LSTMs. They processed tokens sequentially, one word at a time. That created two hard problems. First, vanishing gradients. By the time you'd processed 200 tokens, the model had essentially forgotten what it saw at token 1. Second, no parallelism. You had to wait for step n before running step n+1. That's a GPU nightmare. Attention was the answer to both. The key insight. What if instead of reading left to right, every token could directly look at every other token simultaneously? That's the entire idea behind the attention mechanism. Section 2. Scaled product attention. What's actually happening? Here's the formula senior engineers should have internalized. Attention of Q, K, V equals softmax of Q times K transpose divided by the square root of D sub K, all times V. Let me break that down the way you'd explain it in an interview. You have queries, keys, and values. Think of it like a database lookup, but soft. The query is asking, who's relevant to me? The keys represent each token's advertisement of what it contains. The dot product measures compatibility. The softmax turns those scores into a probability distribution. And the values are what you actually retrieve, weighted by relevance. The square root of D sub K in the denominator is crucial. Without it, as embedding dimensions grow, dot products explode in magnitude. The softmax saturates, gradients vanish, and training collapses. That's why that scaling factor exists. Senior candidates who know this detail immediately signal depth. Section 3. Multi-head attention. Why one isn't enough. Single attention heads see everything through one lens. Multi-head attention lets the model look at the input through multiple lenses simultaneously. Each head learns a different projection of Q, K, and V. One head might learn syntactic relationships. Another might learn semantic similarity. A third might learn positional co-occurrence. You concatenate the outputs and project them down. The practical question interviewers love to ask, how many heads should you use? The answer is, it depends on your embedding dimension. Standard practice is heads equal D model divided by 64. So a 512-dimensional model typically uses 8 heads, each operating in 64-dimensional space. Why 64? Empirically, it works well. More heads aren't always better. At some point, you're splitting attention across dimensions too small to be meaningful. Section 4. Self-attention versus cross-attention. This is a classic distinction that trips people up. In self-attention, Q, K, and V all come from the same sequence. Each token attends to every other token in the same sequence. This is what happens in the encoder and in decoder self-attention for already generated tokens. In cross-attention, Q comes from one sequence, but K and V come from a different one. In a translation model, the decoder's Q comes from the target sequence being generated, but K and V come from the encoder's representation of the source sentence. That's how the decoder reads the input while generating output. In production, when you see slow decoder throughput, cross-attention is often the bottleneck because K and V have to be recomputed or carefully cached across decoder steps. Section 5. KV cache. The inference optimization senior engineers must know. This is where theory meets production reality. At inference time, autoregressive generation is slow because every new token requires attention over all previous tokens. Naively, that means O of n squared compute for a sequence of length n. The KV cache fixes this. Once you've computed keys and values for tokens 1 through t, you store them. For token t+1, you only compute Q, K, and V for the new token, then attend over the cached K and V history. You go from recomputing everything to extending incrementally. The challenge, KV cache grows linearly with sequence length, times batch size, times number of layers, times number of heads, times head dimension, times 2 for K and V, times bytes per float. For a 70 billion parameter model serving long contexts in large batches, that's easily tens of gigabytes per request. This is one of the primary memory bottlenecks in production LLM serving. Senior engineers know to monitor KV cache utilization, implement token eviction policies for long contexts, and consider paged attention. which treats the KV cache like virtual memory with fixed-size pages to avoid fragmentation. Section 6. Attention complexity and scaling challenges. Standard attention is O of n squared in both time and memory with respect to sequence length. Double the sequence, quadruple the compute. That's fine for sequences of a few thousand tokens. It becomes catastrophic at 100K or 1M tokens. This spawned an entire research area, efficient attention. The key variants you should know. Sparse attention, like in Longformer or Big Bird, only attends to local windows plus a few global tokens. Reduces complexity to O of n. Linear attention approximates the softmax attention using kernel methods. Brings complexity to O of n, but typically trades some accuracy. FlashAttention doesn't change the math, but rewrites the computation to be I/O aware. It tiles the attention matrix across SRAM to avoid slow GPU memory round trips. Same exact result, 2 to 4x faster in practice. This is now standard in all serious production systems. In interviews, if you mention FlashAttention and can explain why it's I/O bound rather than compute bound, you're already in the top 10% of candidates. Section 7. Positional encoding, because attention is permutation invariant. Here's a subtle point that interviewers use to probe depth. Raw attention has no concept of position. If you shuffle the input tokens, you get the same attention scores, just reordered. That's a problem. Word order matters in language. The original transformer added sinusoidal positional encodings, fixed vectors added to token embeddings before attention. They encode position as a combination of sine and cosine waves at different frequencies. Modern systems use rope, rotary position embeddings. Instead of adding position information, rope rotates the query and key vectors by angles proportional to their position. The genius: relative positions are preserved in dot products automatically, because rotating by angle A and rotating by angle B gives you a dot product that depends on a minus B. Why does this matter in production? Rope generalizes to longer sequences than seen during training. If you trained on 4K context and need 32K at inference, rope with appropriate frequency scaling gets you there. Fixed sinusoidal encodings just break. Section 8. Interview framework. Answering attention questions. When you get a system design question involving attention, here's your playbook. Start with the access pattern. What's attending to what? Self, cross, or both? Then address the sequence length. Is this a short context use case under 4K tokens or long context requiring sparse or linear attention? Then hit the inference path. Are you doing batch offline inference where memory is constrained, or online autoregressive generation where KV cache and latency dominate? Finally, bring in hardware constraints. Are you running on a 100 with 80 gigabytes VRAM, or are you deploying on edge hardware where FlashAttention style tiling is mandatory for correctness? This framework shows architectural thinking, not just textbook knowledge. Section 9. 3 questions you should be able to answer cold. 1. Why does scaled dot product attention divide by the square root of dk? To prevent dot products from growing too large as dimension increases, which would cause softmax to saturate and produce near-zero gradients. 2. What is the memory complexity of KV cache, and how do you manage it? Linear and sequence length times batch times layers. Manage via paged attention, token eviction strategies, and context window limits per request. 3. What does FlashAttention actually optimize? It's an I/O-aware rewrite of attention that tiles computation to fit in fast SRAM, reducing slow HBM memory reads and writes. It doesn't change the math, it changes where the math happens. Closing. Attention is not just a building block. It's the lens through which modern AI systems process all knowledge. Understanding it at this depth means you can debug degraded model quality, optimize serving costs, and architect new systems from first principles. That's a senior engineer. Not someone who can quote the formula, someone who knows what breaks and why. Tomorrow we go even deeper into production AI. Until then, keep building, keep studying, and stay sharp. This is Agentic AI World. See you in the next episode.